There are a lot of contributors to our knowledge of how electricity works. Many of them have physical constants, units, or laws named after them. The SI unit of charge, for instance, is named after Charles Augustin de Coulomb, while the SI unit of capacitance, the farad, is named after Michael Faraday, and the CGS unit of magnetic field is called the Gauss, after Carl Friedrich Gauss. While I could note that 1 Gauss is 10,000 Tesla, or the magnetic field of Earth's surface is between 25 to 60 microtesla, or 0.25 to 0.60 Gauss, I find that Wikipedia tells me that the Gaussian CGS unit system contains several conflicting sets of electromagnetism units, and therefore ought to be avoided if possible. For now, though, I don't want to talk about magnetic fields, but electric fields. I want to talk about electric fields in 3 essentially equivalent ways, but conceptually different. For the moment, we'll call these the point field, the extended field, and the arrow field. All these ways are equivalent, but conceptually and intuitively different. For the point field, we imagine that a charge Q is placed at a point in an electric field, and it experiences a force of Q times the electric field. So that means that the electrical field is measurable at that single point in units of force, newtons, per unit charge, coulombs. For the extended version of the field, we're going to take that force and assuming the charge is pushed by that force through some distance. So instead of having an electric field at a point, we have sort of an average electric field between 2 plates or between 2 parts of a circuit. So we're sort of multiplying the electric field by meter over meter. And a Newton, recall, a Newton times a meter, recall, is a joule. And a joule per coulomb is called a volt. Now we have 2 fairly common units by which the electric field is described. The point version in newtons per coulomb and the extended version in volts per meter. The arrow version doesn't have its own unit, but is a conceptual tool we can use to get an intuitive description of an electric field lines. Whether we're talking about the extended version or the point version of the electric fields, the magnitude and direction of the field is proportional to the density of the electrical field lines through a given area. Now that I've briefly talked about different ways of describing an electric field, I would like to discuss Gauss's law and its use with a few charge geometries. In our text, Gauss's law is described in this form: electric field times surface area equals charge enclosed divided by epsilon naught, which is the electric permittivity of free space. There is really one big requirement for using this formula. The electric field, E, has to be constant over the surface area A. If I took that requirement away, the equation would take on a different form containing a lot of calculus symbols. Here we have the closed surface integral of the dot product of the electric field and the E and the normal vector n with a differential surface element dA is equal to the volume integral of the density over epsilon naught, the charge density over epsilon naught. But we don't have to look at that right now because we are going to look at 3 cases where the electric field is constant over the area enclosed, namely the point, the wire, and the plane. Before we do that, I would like to bring up this technicality of the relation between Coulomb's constant, K sub E, and the electric permittivity of free space, epsilon naught. These 2 expressions are essentially like reciprocals of one another, except for the factor of 4 pi. I find K sub E to be much easier to remember, being so close to 9 times 10 to the 9th. Also, we'll soon see that K sub E, being Coulomb's constant, has much in common with the universal gravitational constant. Capital G is capital G is Newton meters squared per kilogram squared, while K sub E is Newton meters squared per Coulomb squared. Okay, so now here are the three symmetric geometries that I'm going to use to calculate the electric field using Gauss's law. We have a cylinder/wire, we have a sphere with a point inside, we have a plane bounded by two other planes. We're going to figure out how much charge is enclosed in each of the surfaces. For the wire, we'll ask how many coulombs per unit length. The answer we'll call mu in coulombs per meter. If we multiply the linear charge density mu times the length, we'll have Q, the charge enclosed. Similarly, with the plane, we'll ask how many coulombs per unit area. The answer here we'll call sigma, the area charge density. Multiplying the area charge density by the area, we have the charge enclosed. With the point, we don't have any distribution or density. All of the charge is enclosed right there at the point. Now, for the area of the surface, the wire is surrounded by the walls of the cylinder here, not the end caps, but we imagine the wire continuing for a long ways in either direction. Otherwise, that criteria of constant electric field wouldn't be met. So the surface area of an open cylinder is the circumference of the cylinder, 2 pi r, times its length, L. Likewise, the surface area surrounding a point symmetrically is a sphere with a surface area 4 pi times its radius squared. We also imagine the plane surrounded only on the top and the bottom, not the left, right, front, or back, so that the central sheet of area A is surrounded by two more sheets, each of area A. Now, to each of these geometries, we'll apply Gauss's law to find the electric field. It's quite easily done because for each geometry now we have a Q enclosed, being what's in the top row here, and a surface area being what's in the second row. Okay, now I've got the identical equation for electric field from Gauss's law in all three columns. Notice I'm showing one form with the 4 pi K sub B on the top and another with the epsilon naught on the bottom. Okay, replacing our charge and surface area in each case, I decided it was more convenient to use the K sub E form in the cylinder and sphere symmetry and the epsilon naught form in the plane symmetry. For the wire, we see that the L's cancel, the 4 pi and the 2 pi cancel to get 2. We're left with 2 K sub E mu, the linear charge density, divided by the radius. For the sphere, the 4 pi cancels out with the 4 pi, and we're left with the electric field equals K sub E Q over R squared. This is the most familiar form, and it actually is called Gauss's law in our text. And finally, for the area charge density, the area cancels with area, and we're left with the area charge density divided by 2 epsilon naught. You might think it is strange to say that there is no R dependence on the electric field from a flat plane. Does that mean that no matter how far you get from this flat plane, there would be no change in the electric field? Well, I will say yes and no. If you get farther and farther away from a flat plane, there are two possibilities. Either that flat plane begins to look like a point, or it keeps looking like a flat plane. If the flat plane gets so far away that it begins to occupy a small space in your view, then the equation for the electric field will start to be more like this one, called Coulomb's law. But if you remain where the flat plane occupies horizon to horizon, then the electric field would be constant. This is very much like gravitational fields. If I am in an environment where I see Earth from horizon to horizon, then the gravitational field is a constant, 9.8 newtons per kilogram, everywhere I go. But if I get further away, where Earth looks less and less like a plane, I start using Newton's universal law of gravity. In this sense, gravitational fields and electric fields are very similar. There is one other point that I'd like to make before I go. Here I have given a description of how to find the electric fields for 3 different charge distribution symmetries. What I'd like to do is give a mention of something you can do if your charge distribution does not fit into any of these symmetries and still get an intuitive description of the electric fields. Now I'm talking here about something that I've already mentioned, electric field lines. Electric field lines start on positive charges and end on negative charges. The number of field lines should be proportional to the charge present. So with these two charges pictured, I have drawn 8 lines coming out of the charge labeled plus 2q and 4 lines going in to the charge labeled minus 1q. These lines are joined up together as well as you can to give some sort of intuitive sense of which direction electrical fields ought to be pointing in the region and how strong they might be based on their density. Now, if we get far, far away from these two charges, you would just have the 4 lines coming out, which would indicate a total charge enclosed of plus 1q. Michael Faraday was a pioneer in the laws of electricity using such visualizations of electric field lines. Thank you for watching.